Hey, Math 1 peeps. Today we are starting Chapter 7. Chapter 7 really kind of starts a geometry portion of the year. So we will be breaking into some geometry today. Let's get started. All right, so today we want to determine, we want to look at similar figures, right? We want to look at similar figures. We want to be able to determine if two figures are similar, and we want to find missing measurements. That is our goal for the day. So let's start by looking at what similar figures are. Here is the technical definition. I don't use this a lot, but it is the technical definition of similar figures. Two figures are similar if a sequence of rigid motions, right? A rigid motion is like a translation or a reflection or a rotation. Those are things that we did back in Chapter 3. Those are called rigid motions because they do not change the size and shape. But figures are similar if a sequence of rigid motions and or non-rigid motions, like a dilation, right? A dilation is a size change. You hopefully did that in Math 8 a little bit. So similar figures are if there are a rigid motion or non-rigid motion that maps one figure onto another figure. So if you can like reflect and then do a dilation, those are similar figures. That is the official definition. We don't use it a lot. Similar figures have corresponding parts. Now this is important. This first example is going to be really easy, but it's not always this easy. You should be able to name the corresponding parts. In the diagram at the right, if triangle ABC is similar to DEF, then there are 6 pairs of corresponding parts, and we're going to name them. Angle A would correspond to angle D, right? These two angles match up with each other, right? Correspond means they match up with each other. Angle B corresponds to angle E, and angle C corresponds to angle F. And then we've got the corresponding sides. Side AB corresponds to side DE. Of course, side BC corresponds to side FE. And side AC corresponds to side DF. Okay, that corresponding parts really just means you're matching up the parts. If I were to take this triangle and maybe do a translation so it was sitting right here, and then maybe do a dilation to make it bigger, they would match up with each other. All right. This is the more common thing you should know about similar figures, much more common. They have 2 main characteristics. Their corresponding angles have equal measures. Angles are equal. Their corresponding sides are, big word here, proportional. Corresponding sides are proportional, and we're going to spend a little time talking about that. This, it's funny, I forgot a word in here. I think it's supposed to be the word means. This means that each pair of corresponding sides have the same scale factor. That is something that maybe you learned about in Math 8 last year, but if not, we're going to talk about it anyway. All right, so what is a scale factor? A scale factor is a ratio. A ratio is a fancy word for fraction. That indicates how the side lengths of two similar polygons are related. The scale, okay, this is an important one. The scale factor can be found by writing a ratio between the lengths of any pair of corresponding sides. And the direction matters. So let me show you what I mean by that. I have an example here. Should be an easy example. All right, so if I were doing the scale factor, let's see. Let me say this first. Your ratio is going to look like this. New side, sometimes we call that the image, over original side. Sometimes we call that the pre-image. This is how you write the ratio. So if I was calculating the scale factor, and I was going from, let's say, small to big. So I'm going to do the scale factor from small to big. I would want to put the new side over the original side. So the small would be the original, and the one I'm going to would be the new. So all I'm going to do is I'm going to take two corresponding sides, say the 2 and the 3. Now, since the big one, right, my scale is going this way, it's going from the small one to the big one. The small one is my original, the big one is my new, so the scale factor would be 3 over 2. The new side, 3 over the original side, 2. Or I could use a different pair of sides, right? I could use the 4 and the 6, and it would be 6 over 4. Or I could use the 7.5 and the 5, and it would be 7.5 over 5. Now, they say that these are, let me find it, not there, proportional. Corresponding sides are proportional. And here's why that you guys all know what proportion means, right? A proportion is two fractions that are equal to each other. So look at these fractions. Do these fractions equal each other? Sorry about that. Are these all equal? Well, they are all equal, right? If you reduced 6 over 4, it would equal 3 over 2. If you reduce 7.5 over 5, it would equal 3 over 2. All of these are equal, which is why it said their sides are proportional. We're going to get back to that again in a minute. All right, this is if I was doing small to big. And just so you know, what if I wanted to do the scale factor going big to small? So now this would be my original, and this would be my new. And the scale factor would be, right, new over original. So it would be 2 over 3 or 4 over 6. Because now I'm going this direction. This direction, my scale factor is 2/3. Originally, it was 3 over 2. All right, so what does the scale factor do for us? We're about to see what the scale factor does for us, but this just shows you how to calculate the scale factor. Let's move on. So let me review. How can you tell if two figures are similar? Well, this is the more common way to tell if two figures are similar. All corresponding angles are equal. All pair of corresponding sides are proportional. That is the more common way to tell that two figures are similar. We do, though, have over here We have the original definition. There is a sequence of rigid motions, possibly followed by a dilation, that maps one onto the other. That's true also, but more often than not, we use this first one. All right, we've learned about these similar shapes. Let's learn the skills that we need now to do the homework. First, using the scale factor, proportional, to find missing side lengths. You're going to want to write small here, you guys. All right, so first, how do I find the scale factor? Let's call it SF for scale factor. And let's put myself on a smaller writing thing here. All right, so what I want to do is I want to find one pair of corresponding sides that have measures for both. All right, this is how I find the scale factor. So let me go over here and find the corresponding sides. Now the corresponding sides are a little tricky in this diagram. It looks to me like the 35 matches up with the 14. Like those would be corresponding sides. And then another pair of corresponding sides would be the 17.5 and the X. Now I'm just color coding these. If you're just using a pencil, you might not want to circle them all. I don't know. Maybe just underline two of them or something. Another pair of corresponding sides would then be the Z and the 8. And another pair would be the 25 and the Y. And the last pair would be the 25. Really? 25 for both. Look at that. And the 10. Okay. So if I want to find the scale factor, then I need to use one pair of sides where I have measures for both. And I'm going to go first, big to small. So big to small, I'm going to use the red one, not the red one, the blue one. Is there a better than the blue? Nah, I guess the blue is fine. Going big to small, it would be 14 over 35, which I could reduce to 2/5, or I could make it a decimal, 0.4. My scale factor is 0.4. What if I wanted to go from small to big? If I want to go from small to big, all I do is reverse it, and it would be 5 over 2, or 2.5. All right, I'm not sure I've left myself enough room here. Okay, so my scale factor going this way is 2.5. My scale factor going the other way is 0.4. All right, so what you can do is, the scale factor is good for this. Multiplying the side length of one figure times the scale factor gives you the corresponding side length. So if I want to solve for M, is M one, not M? If I want to solve for X, Y, or Z, let's solve for X. If I want to solve for X, I take the 17.5, I multiply it by the scale factor, which is 0.4, and that equals the corresponding side. So 17.5 times 0.4, what would that equal? That would equal 7. the x must be 7. Let's do one the other way. What if I wanted to solve for z? If I want to solve for z, I'm going to start with the 8, and I'm going to go this way, so I'm going to multiply by the scale factor going that way. I'm going to do 8 times 2.5, and that's going to equal the z, or z would equal 20. That is one thing that the scale factor is good for. Now, I want to show you one other way to solve for a missing side, and I'm just going to set it up because I think it is valuable. Another way to do it is to use a proportion. And when you use a proportion, you set up a fraction equal to a fraction. And you know what? I'm going to do this in the next example where we actually have to do it. Here we go. Corresponding sides being proportional is another way to find missing sides. So let me show you what we're going to do here. The smaller triangle inside the larger one is similar to the larger triangle. So the orange triangle is similar to the blue triangle. All right, write a proportion and solve for x. So we want to set up a fraction equal to a fraction. And I am going to put the small triangle on top and the large triangle on the bottom. And this fraction is going to be the bottom of each triangle, and this fraction is going to be the left side of each triangle. Let me show you what I mean. So, the bottom of the small triangle is 11.2. The bottom of the large triangle is 28. So my scale factor might be 11.2 over 28. That's the same as a scale factor. But I'm setting up a proportion instead. And I have done small over large for the bottom of the triangles. Now I'm going to go to the left side of the triangles. On the left side, the small triangle has a length of x. Now the large triangle, the blue triangle, has a side length of x and 27 added together. So that length is actually x plus 27. And I know that these are proportional because all the side lengths are proportional when the triangles are similar. So I can make a proportion which I can then solve. And I would solve this, of course, by cross multiplying. 11.2 times x plus 27 equals 28 times x. And I could go ahead and solve that. I don't feel like we need to. If you solve it, you end up getting x equals 18, I think. You know, you would distribute the 11.2 and then you'd get the x by itself. I don't want to take the time to do it. All right, so I've done the first thing. I have solved for x. X is 18. Let's put that in for the x. The next thing they want me to do is determine the m. I do want to do this because we have to bring back an old friend. How are we going to find the m? Well, we are going to bring back an old friend. I hope you know this. Solve for m, and we are going to use the Pythagorean theorem. Do you remember the Pythagorean theorem? In a right triangle, leg squared plus leg squared equals hypotenuse squared. Or in this one, that would be 18 squared plus 11.2 squared equals m squared. I wanted to review the Pythagorean theorem with you because it will come in handy sometimes when we're dealing with right triangles. So I would go ahead and square these and add them together, and I would get 449.44 equals m squared. And then I would take the square root of both sides, and the square root would be 21.2. And I now have that this is 21.2. All right, I just wanted to remind you of the Pythagorean theorem. I am not going to solve for p for the sake of time. All right, the last thing we need to do, really easy, is the definition of congruent instead of similar. Figures are congruent if there is a sequence of only rigid motions. Only rigid motions that map one figure onto the other one. So the difference is similar figures can change size. Congruent figures cannot change size. They have to be identical. Two triangles are congruent if all three corresponding side lengths and all three corresponding angle measures are equal. And I just want to go over one thing with you on congruent. When writing a congruence statement, the order matters. And I just want to go over how to make sure you put the letters in the correct order. So we're going to do this example. Jackson wanted to write a congruent statement saying that the two triangles below are congruent. He started with triangle M and P, but he got stuck because the triangles were not oriented the same way. He could not tell what matched up with what. Can you tell what matches up with what? So this is what we're going to do. We're going to start with his statement. Triangle MNP. And then we're going to put the congruent sign, right? This is the congruent symbol. It's an equal sign with a little wave over top of it. And what Jackson is trying to figure out is how to name the other triangle, because he has to put the corresponding parts in order. His first letter needs to match up with the M. Which letter matches up with the M? That's the one that needs to go first. And one way you could tell is that the M is between the 20 and the 8. So over here, the letter that's between the 20 and the 8 is the U. U must match up with M. Those angles are corresponding angles. And like I say, the order matters here, right? The order matters. You got to put the letters in corresponding order. What matches up with the N? Well, the N is between the 20 and the 16. So that would be the W over here between the 20 and the 16. W should go next, and then obviously U would go last. They are now in corresponding order. All right? So we have learned how to set up a proportion. We have learned how to use the scale factor. We talked about the Pythagorean theorem. And we learned how to write a congruence statement and put things in the correct order, corresponding parts. Homework's on Delta Math. I'll see you guys next time.